Parallel plate capacitor. The biggest misconception that goes with this terminology is that people generally understand that the plates of the capacitor are must going to be plain only. No, it's not the case. The only thing is that whatever the type of plate we are choosing, they must be parallel. It's not a binding that both the plates should be equal in size. You see, you might take a disc like coin. You might take a rectangular paper. This is also going to be a parallel plate capacitor. So first of all, we must know what this terminology means. Only condition is that the two conductors should be parallel to each other. One might be having circular shape, circular cross section, and the other might be having rectangular or square. One thing. Second, in this condenser, if we are going to consider the area of condenser, it shall be only the overlapping area. For example, I'll just give a demo. Suppose I have chosen the two plates like this. So, the fingers are exactly opposite to my palm. Effective area of this condenser is going to be overlapping area only. So, second important thing with this condenser is that here we consider only the overlapping area of the plates that we have used. But for simplicity, let's suppose that the two plates are parallel. Their surface area or the overlapping area or the common area or the effective area is A. Distance between them is D. Once you give the charge Q, here it will be minus Q. Then you could calculate the field between them. The electric field between the plates will be Q upon, E is given by sigma upon epsilon naught. You already know if there are two equal and opposite plates or sheets, the field between them, like this. Here sigma is Q upon A. And if you want to find potential difference here, it will be the product of E and D. E and D, it becomes Q D upon epsilon naught A. Q upon V, it's going to be capacity, and you get the result epsilon naught A upon D. That is the capacity for the parallel plate condenser. But here we have calculated the capacity without considering any medium. Medium is always obviously between two conductors. You can't have the choice of putting this or filling this by one conducting material. It should be some insulator. If you use some insulator, or you might call it dielectric, then in that case we see that capacity is going to be K times. You could say when we fill up the space between the two plates, that of the condenser, the capacity increases to K times. It is C naught into K. Now, three things with this electrical capacity. One, it depends on size, it depends on the medium, it depends on the conductor in its vicinity. So, here in this condenser, you see the capacity is being affected by the dielectric that is placed between the two. Here you must remember that whatever the charge you give to the plates of condenser, it's not going to reside on the dielectric slab. Suppose this is the slab. You have completely filled the condenser. Charge you give over here, this charge will not be transferred to the slab or the plate. On the conducting plate, minus charge is developed. within the dielectric slab, polarization takes place. So you can never say that the charge that is given to condenser reside on the dielectric also. That is wrong statement. Whatever the charge is supplied from the source, that resides only on the plates. What happens within the slab, that's another process. We'll look into detail of it. Suppose you are filling the space between the two plates by many slabs like this. There are many slabs. Then in that case, simply the capacity would be given by d minus T1 plus T2. It will depend on, here just suppose there are only two, then this is the relation. Then d minus t plus t by k, it should be t by k here, T1 by K1, T2 by K2 is like that. You can have T1 by K1, T2 by K2. If it is filled by many dielectric slabs, the total capacity is going to be of this nature. Here, if you are having 3, then in that case here also you can have T3. Sigma T you could use in a better way. Sigma T by K we could use in the place of this whole bracket. Now another thing is we are going to have one metallic slab. Metallic slab. This is suppose of thickness T. Then space left for condenser is this only. In that case, capacity is going to be d minus t. You must remember this relation t by k. This relation t by k here, you see, k is infinity for the metals. Infinity for the metals. Then this will be 0. Anything upon infinity that becomes equal to 0. C is equal to epsilon naught A upon d minus t. This is the formula for metallic slab being introduced between the two plates. Say this is D. One more interesting case, if this metallic slab is very thin, it's like sheet, then T would be 0 and you could say the capacity of the condenser is going to be unchanged, because in place of T in that case you will take 0. One more thing, within the two plates of condenser, you are having two metallic plates, thin plates, and you have just joined the two plates. Now what will happen? This is no more a condenser. This entire space is useless. So you could consider the effective thickness, if it is T, then in that case, the effective space left here will be d minus t only. So C is equal to epsilon naught A upon d minus t. Again, so you see the two cases are similar. If one T thick metallic slab is used or two thin metallic sheets are used and they are interconnected, in both the cases you are going to have the same relation. Now, when the condenser is charged, both the plates are having equal and opposite charges. Both are opposite, obviously they will be having some force of attraction. And if there is force, there will be pressure. Pressure between the two plates, force between the two plates. Pressure, you know, is given by sigma square upon 2 epsilon naught. If you multiply this by area, pressure into area, that's pressure, force. For getting the force, you'll have to apply this relation and then multiply it by area. You might convert this thing into Q upon A, it will become 2 epsilon naught A square A force. What is important here is either you remember this relation or even this also, Q square upon 2 epsilon naught A. In both the cases, you find that force is exactly independent of the distance between the plates. This is important result. The force between the two plates of condenser is independent of the distance, whereas in Coulomb's law, the force between two charges always depends on the distance. Even the force between the two dipoles also depends on the distance. So here, when the force is not depending on the distance, if you bring a dielectric slab near the charged condenser like this, soon as this slab is brought near the mouth of the condenser, polarization will take place, here minus and here plus. Attraction would take place. The slab will be attracted, it will go inside, it will come out other side, and the whole process will go on repeating. Ultimately, it's going to be oscillatory motion. But since the force must be proportional to the displacement, this is one of the most important conditions of simple harmonic motion. Here the force between the plates of condenser, the force is not depending on the distance, it is independent of the distance. So you could say it will oscillate, but it's not going to complete simple harmonic motion.